Errors in electronic distance measurement instruments. The topics that we'll discuss in this video include slope distance reduction to horizontal distance, the reflector or the prism offset constant, atmospheric temperature and pressure issues, and erroneous frequencies in the EDM instrument itself. The first systematic error that we'd like to discuss is slope distances converted to horizontal distances. All EDM observations are slope distances, so we must correct the slope to the horizontal, and we use simple trigonometry for short lines. What we mean by short line is a line that can be used in plane surveying. In other words, earth curvature and light refraction are not issues in the analysis of the horizontal line. We can go about determining the horizontal distance two ways. One is using elevation differences. In the sketch, we can see that the horizontal distance right here is one side of a right triangle where D is the other side and L is the hypotenuse. And so we can simply say that L squared is equal to H squared plus D squared. And if we solve that equation for H is nothing more than the square root of L squared minus D squared. So L is the slope distance, and D is this vertical dimension between the center of the reflector to the center of the instrument. Now we can determine this distance D by looking at the elevation of the point A, where the EDM is set up, the elevation of point B, where the reflector is set up. We can also look at the height of the EDM instrument with respect to the surface of the Earth, and the height of the reflector with respect to the surface of the Earth. If you take those four quantities into account and solve for D, you can see that D is equal to the elevation of A plus the height of the EDM instrument minus the quantity elevation of B plus the height of the rod. This method is okay if you have the elevation of point A and the elevation of point B. However, many times in EDM measurements, we do not have that information, and so we need to proceed with a different method. The other method is the use of the zenith angle Z. In this sketch, we can see that we really don't have the height of the reflector is not known, the height of the instrument is not necessarily known, but what is known is this zenith angle. The zenith angle is one of the elements returned by the total station to the user in the measurement process. So zenith angle is always measured and reported. L is always measured and reported. And so what we can do is just focus on this right triangle right here, and we can see that Z helps us compute the side H. H is equal to the L times the sine of Z. And this is the method that is used by the total station to return the horizontal distance to the user when the horizontal distance is requested. The second systematic error is the reflector prism offset. In the reflector prism offset, we're looking at what's happening here in the prism in the EDM measurement process. Here the EDM is issuing its wave, and the wave comes to the prism. It travels through the prism glass, reflects off of the surfaces here, comes back out, and then returns to the EDM instrument, and the measurement is determined by the EDM instrument. What we want to do is we want to focus on what's going on in the prism right here. So we can see here the blue line, the blue rectangle, represents the prism with a depth of D, and these other blue lines represent the surface of the reflector itself. And so the electromagnetic wave from the EDM travels in through the reflector on path A, bounces off, travels across path B, and returns back out across path C to the EDM. So light travels the path A plus B plus C, and it's equal to 2D. The light, however, travels slower through glass than air, and we have to make some accommodations for that. The index of refraction of glass with respect to air is 1.517. So, in effect, the center of the reflector right here is really, in effect, back behind the prism itself, a distance of 1.517D. And so we must make an adjustment for that, and that adjustment is this K value right here. The effective center is behind the prism. So what about this K value right here? We need to know what that dimension is. Well, K is the location of the effective center with respect to the plummet line which goes through the prism pole. These values range from 30 to 70 millimeters depending on the manufacturer. Some prisms can mechanically flip from 0 millimeter offset constant to 30 millimeter. It's simply a screw mount where you can unscrew the prism, turn it around, and screw it in on the other side, and you'll essentially flip a 30 millimeter offset constant to a 0 millimeter offset constant. K is always subtracted from the measurement, so we would have to take our slope distance measurement and subtract off K. Now, if we're running a total station like we see in the picture here, things become much easier. The prism offset constant is entered by the user prior to making measurements through the keyboard. So the user will be prompted for prism offset constant. The prism offset constant will be entered, and the total station will automatically remove the K offset from each measurement in the measurement process. The third systematic error that we're going to discuss is temperature and pressure. Temperature and pressure affects the index of refraction of light. So as temperature varies and pressure varies, index of refraction of light changes. Well, this modifies the wavelength of the electromagnetic energy, and the temperature and pressure must be measured and used to correct the observed distances. So using total stations, temperature and pressure is input through the keyboard. So again, the use of the keyboard on the total stations helps us remove this systematic error. The total station will make the adjustment to the measurements before the measurement is displayed, and so the systematic error will be removed by the total station. Here is a graphic that illustrates the effect of temperature and pressure error as we make an error in a pressure reading. So for instance, the dashed line is the pressure line. If we make an error of 25 millimeters of mercury, we can see that at 25 millimeters of mercury, we have a ppm error of minus 10. Negative 10 parts per million. And if we make a 50 millimeter error in pressure measurement, we can see that we're around minus 18 parts per million. Likewise, for temperature, we can see that for a temperature error of 10 degrees, we make a 10 part per million error in the distance reading. For a negative 10 degrees, we make a minus 10 parts per million error. So they're both linear functions. To look at what this means in terms of distances measured, just look at this table and we can see that from distances from 50 to 5,000 feet, with the ppm error being from 10, 20, or 30, we can see that this error increases as we go diagonally across the table. So our error is really small for the 50-foot distance. It's insignificant right here. It's insignificant at the 20 part per million error, and it's really insignificant at the 30 part per million error. But as we travel down through the data, we can see that around 500 feet, the error starts to creep in, starting to make some difference in the hundredth place, which is typically what we measure our distances using the EDM. And so at 20 parts per million, definitely making a difference in the measurement, and at 30 parts per million, definitely making an error. As we go up to 1 mile, we can see that this is 5/100ths of a foot error at 10 parts per million, 10/100ths, 15/100ths error. So the longer the distance, the bigger the error. And again, it's just a good practice to always enter the temperature and pressure in the total station prior to making measurement. The last systematic error that I would like to speak about is the EDM erroneous frequencies, faulty wavelengths in the EDM measurement process. In other words, the EDM instrument itself generates a false frequency, or a frequency that's out of calibration, and the wavelengths in fact become longer or shorter. And so as the wavelength becomes longer or shorter, the total distance measure is going to have a problem. So the maladjustment of the instrument generates the erroneous frequency. This results in faulty wavelengths that degrade the measurements. And this is not a common issue, but the total station should be checked regularly. And how do we do that? Well, we use an NGS first order baseline for comparison. These are baselines of approximately 1 mile in length on relatively flat area, and has varying distances of measurement along that line to calibrate your instrument. If the instrument is found to be out of calibration, then the instrument should be sent back to the manufacturer for adjustment. In summary, the topics on systematic EDM errors include the reduction of short slope lines to the horizontal, the reflector offset constant, K, the temperature and pressure effect of the atmosphere on the measurement, and EDM instrument erroneous frequencies causing faulty wavelengths. The outcomes that we hope you take away from this learning video is that you understand how to remove systematic errors related to slope, prism offset, temperature, and pressure, and you're aware of the potential for erroneous frequencies in the EDMI, and you know how to check for such. This is the end of this learning video.